Now that we've looked at solving differential equations and real-life applications with growth and decay, we'll now actually get into some more examples. At the end of this lesson, you'll be able to solve exponential growth and decay problems. Alrighty, the exponential growth and decay model, when something is growing, basically what it is doing, it's changing with respect to time, so that's how it is involved in a differential equation, and every single time something is growing or decaying, the basic differential equation is going to have the same setup, so when I go to solve that differential equation, the solution will always look very similar, and you'll notice if you look at this problem right here, on the previous video, when I solved that first problem, that's exactly the same equation that I came up with. So what we will be able to do in this video and on these types of problems is appreciate the calculus that went behind getting this formula. And if you'll notice, if you remember the PERT formula when you're dealing with compound interest, that's where the PERT formula came from. It actually came from a differential equation that somebody solved, and that's exactly what we're going to be doing here. So when we have something that is growing exponentially or decaying exponentially, we will be able to use this formula without having to do the calculus behind it every single time. So we're going to go ahead and jump right into some problems. Right, example 2, suppose that 10 grams of the plutonium isotope, Pu-239, was released in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay to 1 gram? And we are going to keep in mind that the half-life of plutonium is 24,360 years. So what we're going to be doing, we know that plutonium is being cut in half, so it is exponentially decaying. So as soon as I see that, I can go ahead and appreciate the calculus behind this formula, but just use this formula, y equals c e to the kt. And now what I'm going to be doing is finding the information. In order to use this formula, I need to figure out what c is, and I need to figure out what k is. So the first thing that we're going to do is we will find c, and then we will find k, and then we will solve the problem, see what's going on with the problem. Okay, so the first thing to find C, I know that 10 grams of the plutonium isotope was released in the Chernobyl nuclear accident, and we will assume that it was released at time equals 0 right when the accident occurred. So we know that there were 10 grams at time 0. Okay, k times 0 is 0, e to the 0 is 1, which leads us to find out that C is equal to 10. So we're now going to have y equals 10 e to the kt. So we have found C. My next thing to do is to find k, and I'm going to try to use information in the problem to help me get there. Okay, I'm going to use the information that the half-life of plutonium is 24,360 years. That means in 24,360 years, half of what I'm starting with would remain. So instead of having 10 grams, I now would only have 5 grams, and that took 24,360 years for that to happen. Okay, from this information, I can solve for my k. So first thing I'm going to do is divide by 10. 5 divided by 10 would give me 1/2, and then I'd still have e to the k times 24,360. All right, at this point, I would like to solve for k. And thinking back to last chapter, if we would like to solve for the variable and the base is e, we can take the natural log of both sides. So I'm going to take the natural log of 1/2, and then it will equal. And then remember, when I do that, I can bump the power out front. So I'm going to have k times 24,360 ln e. And then hopefully you remember that the natural log of e is just 1. And so now from here, if I would like to, I'm going to put this in parentheses just so I know it's the whole thing being natural logged. If I would like to solve for k, I basically just have to get rid of multiplying by 24,360, I will divide by that. So I know that k is equal to the natural log of 1/2 over 24,360. Okay, so now rewriting my equation with all the information that I have now, we're going to have y equals 10 e, and then instead of my k, it will be ln 1/2 over 24,360 t. Notice that I'm not trying to find that out as a decimal right now, because if we round in the middle of the problem, we'll get rounding errors at the end, and that could actually make a big rounding error when I'm all done. So I'm just going to leave it exact until I'm all the way done with all my calculations. All right, so we've now got a formula. The reason that we got the formula was so that we can now answer the question. It says, how long will it take for the 10 grams to decay to 1 gram? So I want to know, how long is it going to take the 10 to now become 1? So now I'm going to be solving for t. So I've got 1 equals 10e to the ln 1/2 over 24,360 t. First thing I'm going to do, just like I did over on the other side, we'll divide by 10. And 1 divided by 10 is 0.1, and I'm allowed to put that as a decimal because it's just a terminating decimal. So I'll get e to the ln 1/2 over 24,360 t. And then just like what I did on the left side, we're going to take the natural log of both sides. So the natural log of 0.1, and then equals this whole exponent I can put out front, so I'll get ln 1/2 over 24,360 t times ln e, and we know that the natural log of e is 1. And now to get t by itself, I could divide by this, but actually I think it will be easier if I multiply both sides by the reciprocal of that to get rid of it. So I'll do the same thing over on this side. Okay, and then we'll get t equals, at this point in time, now I can grab my calculator and I will plug this into my calculator, and when I plug that into my calculator, I will get 80,922.168 years. So if I just started with only 10 grams, which is not a lot at all, from the Chernobyl nuclear accident, it would take 80,000 years for that to decay to 1 gram. So if you can just think of all of the grams that were actually released in that nuclear accident, that's why Chernobyl has such a big mess. All right, let's take a look at example 3. One model for the way disease dies out when properly treated assumes that the rate dy dt at which the number of infected people changes is proportional to the number y, so it is exponentially decreasing. The number of people cured is proportional to the number that have the disease. Suppose that in the course of any given year, the number of cases of a disease is reduced by 20%. If there are 10,000 cases today, how many years will it take to reduce the number to 1,000? So this would be one where you're trying to treat the disease and you want to figure out how long is it going to be till that disease is not a threat anymore. So since we know that it's changing at a rate which is proportional to the number, we know that it is exponential decay, so we can go ahead and write our formula, y equals ce to the kt. Just like we did before, we'll find c, we'll find k, and then we'll actually solve the problem or answer the question that was posed in the problem. Okay, so the first thing, we know that there are 10,000 cases today. So at time 0, there are 10,000 right now. So we're going to put 10,000 equals c e to the k times 0. 0 e to the 0 is 1, so we know that c is 10,000. Okay, so we found c, so y equals 10,000 e to the kt. Next thing is to find k. All right, we know that the number of cases of disease every year is reduced by 20%. So I could say after 1 year, if it's reduced by 20%, then there should be 80% of the 10,000 that still would have the disease. So 80% of 10,000 would be 8,000. So I could put after 1 year, so time would be 1, after 1 year, 8,000 people have the disease. All right, so from here, just like what we did on a previous slide, we can divide both sides by 10,000. That will give me 0.8 is equal to e to the k. And then from here, we can go ahead and take the natural log of both sides. So I'll have the natural log of 0.8 is equal to, bump my k out front, so k ln e, ln of e is 1. So I know that k is equal to the natural log of 0.8. All right, rewrite my equation now. Y equals c, which was 10,000, e to the ln 0.8 t. And then from here, we've got everything ready, so now I'm ready to solve the problem. It says, how many years will it take to reduce the number to 1,000? So I want to know, when will my y value be 1,000? So from here, we've got 1,000 equals 10,000 e to the ln 0.8 t. We'll divide both sides by the 10,000. And that will leave us with 0.1. So we'll get 0.1 equals e to the ln 0.8 t. And then, just like what I'm used to, I'll take the natural log of both sides. So we'll get the natural log of 0.1 is equal to, bring my power out front, ln 0.8 times t, and then ln e. And the natural log of e is 1, of course. So now I have ln 0.1 is equal to ln 0.8 times t. And if I'd like to solve for t, we can just divide both sides by the natural log of 0.8. Again, notice I did not grab my calculator until the very end of the problem. So now I can take the ln of 0.1 divided by the ln of 0.8, and when I do that, I will get t is equal to 10.319 years. So that's how long it would take that disease to reduce to the number of 1,000. So hopefully now you can solve an exponential growth and decay problem.